So we can start. A very good evening to all of you. So today we have Professor Anurag K. Srivastav, who will be giving a lecture today. He holds the Raymond J. Lane Professorship and serves as a chairperson of the Computer Science and Electrical Engineering Department at West Virginia University. Additionally, he is an adjunct professor at Washington State University and senior scientist at Pacific Northwest National Lab. He earned his PhD in electrical engineering from Illinois Institute of Technology in 2005. The research of Dr. Srivastav is focuses on data-driven algorithms and tools for cyber-resilient energy systems. So his impactful research projects have resulted in the implementation of tools utility control centers supported by over 66 million in funding from entities such as US Department of Energy, Siemens, Corporate Research, Electric Power Research Institute, etc. He has held visiting positions in organizations including the Receive the Transport the Electric in France, RWTH Aachen University in Germany, Peak Reliability Coordinator. He is an IEEE Fellow, recipient of IEEE PSPT SOR Educator Award, numbers of Best Paper Awards, leading multiple IEEE Technical Subcommittee, power system operations, resilience, microgrid voltage stability, distributed optimization, and an author over 425 technical publications, 3 books, and 3 patents. We are really privileged to have Sir here for this particular session. So I welcome you, sir, and it's over to you to start the presentation.
Thank you so much. So it's my pleasure to be here. And, because we just heard about IEEE bulk power system operation, that's a committee that I chair. And within that, we are also thinking that what are the changes going on in the power grid and how the operation and control will evolve. So some of my talk will be starting with basics, or we probably already know, but we'll quickly get into that. What are the different things that's going on in the power grid right now, which will require us to put new tools in operation and control, right? So let me just share my slide, if you can allow me to share. Okay. So let me start with this. Can you see it okay, my slides?
Yes, sir, it is visible.
Okay, good. Yeah, so the title of the talk is more on the data-driven power system operation, but let me start with the first challenges and what's ongoing changes in the power grid. So first one is grid operation, and if you look at the way we operate, what we do is that we put sensor throughout the grid, right? So you do have a generation, you have a transmission, and then a substation, which is at both the end, generation substation, and then also a transmission substation. And then we come to the distribution line, we have a distribution substation. And then from there, we get to the, basically consumers or industry or different kind of load or buildings. And sometimes we have a transformer on the pole because that's lowest voltage. And of course, all the substations have a transformer. I'll talk about things are changing, like we have more polytronics based solid state transformer, so those does require a little bit rethinking of the power grid operation. But conventionally, that the way we do it is we put sensor everywhere in the power grid. We take these data to 3 different control center, right? So first we have a local, which is basically these kind of right here, like local control center, right? which is a control room, we call it, at substation, and then we collect all the data there in that substation. And then from there, we send it to the control room. So control room are three different kind. Of course, there is a one transmission control room or control center operation. Then we also have a distribution system operation. If it's a big plant like nuclear and hydro, especially nuclear, we will have a nuclear power grid operation center. And actually, there is one more, which is not for the power grid operation, but for the, like a security operation or network operation center. That's why we are collecting the cyber data or IT management, right? So there are four different kind of control centers. And all four have the same objective, that situational awareness, which means that what is the state of the system that they are monitoring. So again, if it's a generation operation center, it will look at that generation is operating as it should. If it's a transmission operation center, it will look at the transmission system, the way it is operating is good or bad or need emergency control. So this is all part of situational awareness. And then the second thing is that if something is going wrong, then we need a tool to help operator to make a decision. Okay. Now, of course, there are some automated control, which is already in place for frequency control or voltage control. And then we do have the control, which is operator in the loop, which means that operator has to give the command, right? All the protection is the first line of control and the fastest, the relay. And then there are primary, secondary, tertiary control, which will respond within the system. And then the slower control is the one that we take here. And then there are multiple layer of control, which is coming out of this decision support. So first change that is happening are emergency situation, right? So for example, cyber attack, solar storm, which is solar flare, which creates electromagnetic impact on all the electromagnetic devices, all the power grid component, either it's a transmission line or even substation, communication equipment, they all get impacted by electromagnetic pulse. And we do get electromagnetic impact through the solar flare. So, and then we do have hurricanes, we do have a snowstorm, we do have a high wind situation, and or just the rainstorm, right? So all these different event basically stress the power grid component, which means that operation also becomes tricky during that time if we don't have a tools and we don't have a control in place to monitor and handle the power system when these kind of extreme event happens, right? So this is the first kind of change. We are seeing more and more extreme event compared to what we used to see in the past. And the impact is more because our grid, our power system is more connected, right? So and more real-time control. So a lot of things that we used to have a slower control is moving towards a real-time control. And those real-time control means like we are more connected. Cyber system, which is supporting, which is bringing the data, which is processing it here, then sending it here, and then sending it here, and the control is coming back. That's what everything is cyber system, which is the digital data. The first transition that happens here or here, and then all the way that it goes back, and then again we convert it to analog signal and provide it, right? So this transition from analog to digital, and in the digital world, the timeline of digital world is really fast, right? So everything happens in millisecond. Data packet reaches from here to here in milliseconds. While in the power grid, things are happening also very fast, especially electromagnetics kind of signal, but we were not responding fast enough. But because we have advanced the communication and computing, Now we are responding fast, and that does have an impact. So any kind of these extreme event happens because now we are connected more and more dependent on the IT and control, which takes the disturbance also at the faster speed. If you respond slow, then you will be impacted less actually, which is a problem here, right? Which is a challenge here. But if you respond fast, the whole system will be impacted more, right? So that's a kind of like dilemma that, how to design a control so that it will not cause us to be impacted more, right? But now the opposite thing, and that's why it's a dilemma, because the opposite thing is if you don't respond fast, our decision support will not be strong, right? So if you can respond fast, if the control respond faster to any these event, any disturbance, minor or major, we will be able to minimize the impact also, right? So by connecting more, we are impacting more because that's how cascading happens. But by connecting more and by responding fast, we are also responding and mitigating faster. And objective of this whole power grid operation is, always remains the same, right? So goals, either with these changes, with these extreme event, more stressor point, we always want reliability, right? So reliability is again the ability of system to keep supplying power to connected load, right? So that tells us how reliable we are. It could be against unexpected, but normal failure. So we are only talking about normal failure, which is like, this pole has failed, transformer has failed, transmission line has went out. So all those things are normal failure, which is nothing like these, right? So if these things happen, then we are not in reliability zone. We are in security or resiliency mode, okay? So reliability is about the those things which happens often and normal. If it is a failure large enough, then we are not in the reliability mode. And then economics, which means that every time we do the grid operation, it's run by a company, run by a state agency. We want to operate the grid in the most economic way, so that everything that we operate, customer are the one which will pay for it. Sometimes government will also do or pitch some money, but economics will guarantee that customer pays the minimal bill. So economics is very important for service provider and customers. Stability, we want to operate the grid in the most possible stable way, which means that voltage is almost constant. It can vary a little bit, but not going outside bound, right? So small signal stability, tangent stability, or dynamic stability, all these things, frequency stability need to be met while operating the grid, which means that keeping those things within the band. Of course, stability could be extreme, which means that it can collapse. And that brings the whole system down, and that's why we put the stability control in place. Then other thing is security aspect, and which we call it operational reliability, but it basically refer to the failure which is not normal, which means that there are more things failing in the system. And security, a power system security concept is basically saying that even with the failure, our system is reliable. Now, there is a fine line between event, which is impact the security region, versus reliability versus the resiliency. So normal failure is reliability. Failure which happens but not very often, like a line outage, transformer outage, is comes into the security. And then extreme events like these comes into the resiliency. Then there is cybersecurity. So of course, as we put more and more digital system in the grid, we are using the cyber to operate the grid, and we need to make sure that those are secure. So that's a cybersecurity concept. And then sustainability, which is very important, that not only we are able to provide power in reliable way now, but also in the future. So the generation sources are limited, whether it's a hydro or coal or nuclear or renewables. We need to operate in such a way that we have a future energy availability for future generation, and that's the sustainability. Resiliency, we already talked about that. It's a next step from reliability to security is the next step, and security to resiliency is the next step. These are the normal failure. These are the plant failures, which we know, which happens often, but not very often. And these are the rare event that happens once in a year or once in several years. And these are the extreme weather event and cyber attacks. So these objectives basically, take us to that. How do we operate the grid? So we put SCADA, Supervisory Control Data Acquisition System, with the economic and reliable operation goals, which includes SCADA includes sensors in the system, CTP, PMU status. PMU sometime is part of SCADA, sometime it's not, because it has its own softwares, its own communication and networking. So it might be a different system that we call it, but eventually it's also helping us to bring the data and then control. Control is very rare with the PMU, but there is example where PMU is being used for the control. Switch status, again, another example of sensor. Then we have a remote terminal unit. We have a PDC merging unit, a PDC R merging unit, which will bring the data from PMU as a PDC. A communication system, data archival historian, all the part of SCADA. Then we have software in the control room, which is like a stress estimation, control center display, visualization tool, and then alarm and alerts. And for decision support, which is the next thing, that if something goes wrong, then it's all about different timeline, right? So real-time operational, which means like, as fast as possible at the same speed as the power grid. In millisecond real-time operation support, then short-term planning support, and then long-term planning support. Now, even the long-term planning, it is supporting the decision support in the power grid, right? So we do something so that even if it fails, we are prepared to how to keep the system economic and reliable. So time frame could be seconds, minutes, hours, day, and month. Again, there are some software which will give us the control signal. Sometimes we solve the OPF, sometimes we just go the rule base. But optimal power flow help us in unit commitment, which will be here, and short-term planning. Economic dispatch will be real time. Hydrothermal thermal scheduling will be long-term planning because it goes in several months. Then security analysis, we already talked about security, which is ability of the power grid to still be reliable and keep supplying power to all the connected load, even with some failures like transformer and generation and transmission line failure. If the failure is several number of components, then we go into the resiliency mode. But before that, it's a security. And then load and price forecasting. Of course, that's a part of the software and the cost of operation. Energy interchange with the neighboring area. And then sometime if you have a market, then we do the market power analysis. So these all are part of the EMS, Energy Management System, or ADMS, Distribution Management System, which will have slightly different functionality, but it does exist, in the same way like a control support or decision support in a different timeline. And then comes the very fast thing, which is automatic control. Like I said earlier, the protection is the fastest one, automated control. If we see the fault, we need to isolate. And there's no exception in that. So protection is the fastest. Then the droop control, which will look at the frequency, and then use the droop control to basically increase the generation in such a way in automated manner. That's a primary level of frequency control. Then we have automatic voltage regulator. We have automatic generation control. And not everything need to exist. And even if it exists, it's not need to be operated in the system because we have been operating without AGC some generation, which is okay because there are some other generation which will be able to control it, right? So every power grid is different. Some control is there, some are not. So other than generation control, we also have a remedial action scheme, which is kind of last line of automated defense. And we also have an under frequency load shedding. So if a frequency is very much gone out of control, then we have to shed the load. Sometime we put this control in the place, which will automatically isolate the load because frequency is lower. It means that load is high, generation is less, so you have to isolate the load. Different parameter we're looking at is that, of course, voltage, frequency, and power flow to make the automatic control work. So now let's talk about changes. So these things are in place, but things are changing. We still have a same generation transmission, step up down transformer and step up transformer. And then we have a different kind of customer. So same thing, same structure. But now we have a different kind of generation more and more, which is a renewable generation. More solar, more storage, more wind. Here in the customer side, we have energy storage, we have electric vehicle, we have a rooftop solar, we have a demand response, we have a smart thermostat, smart charging. Sometimes we have a community solar, which a community will decide to put the solar. We also have a thermal load, which can respond as a demand response. We also have a solar water heating. We have a same building with a battery, thermal, solar, all combined together. And then at the same load side, we have a DR, distributed energy resources, which is again solar, wind, batteries, EV charging station. Sometimes we have generator, backup generator, which can be used as a part of the grid, or it's just independent and it will only operate at the building level. Thermal storage, UK has a lot of thermal storage. Cogeneration, we have sometime. Hydroelectric, which is run of the river plant, which will be at the city level. And then, a lot of different kind, fuel cell, and even more advanced, I have seen buildings which is called net zero building, which will have even curtains with the solar panel, which will work in the daytime because curtain is closed and will help to get to net zero solution. So renewables, extreme event, demand response, changing communication, computing are some example of control, right? And these renewables are increasing a lot. If you look at the EIA, Energy Information Administration 2025 report this year, we will see that, they predict that by 2040, we'll have a very different mix, right? So here is the 2018, which is slightly increased in 2040, which is the oil-based, the natural gas-based. It will be changed. Coal will become even further reduced, right? Other renewables will increase a lot. So you can see that it's a lot more. And then bioenergy will increase, nuclear will increase a little bit, biomass will be almost the same, hydro will increase, right? Of course, if you look at the percentage wise, we still have gas and oil based highest, and then renewable will be there, but not even by 2040, it is not going to be higher than other generation, which, but it will take time. Eventually we'll get more and more. And year to year global change in electricity generation, which means the load is changing and the generation is also, right? So, like coal went down in 2020, but then 2021 it came back. And again, this is the net change. It's not the absolute value. And what is increasing a lot, you can see the green part, which is the renewables, right? So this has increased every year. Doesn't matter that what year we look at, 29 to 27 prediction. So with these changes, we also have a different operational challenges, right? So one is very famous, which we call duck curve. Duck, it looks like a duck, that's why. So which means that the power, which used to be the load profile, which used to be like this, right? Which is one peak here in the morning, one peak here in the evening when everyone comes to the office, and one peak where everyone goes to the house. So you typically have morning and evening peak. Now it's not necessary because every uh, system load that we're looking at may have a different behavior. But with the renewables, what is happening is that in the daytime, we will have solar and other renewable energy reducing the load, right? Because we can provide the load locally with those solar, so it will go down. So the load demand to the grid will go down because it's a behind the meter or smaller solar, which is taking care. So it will go down, and you can see that this is a real curve from the California ISO. So 2013 it was like this, 2015 it became like this, 16, 17, 18, and then 20, and it's the valley is going further and further down. Why? Because the load will reduce as we put more and more solar near the, or even battery near the load. The challenge is that when evening comes, in the evening around 5 p.m. or 6 p.m., when the sunset happens, then the load suddenly increase. And these kind of ramp, not all the system can sustain because this is too fast. So we only need a faster generator to respond to that, right? Of course, like nuclear cannot respond, hydro cannot respond, gas can respond to this, battery can respond to this. So if we don't anticipate these kind of ramp rate and are not proactive, then we cannot sustain the grid. So what we can do is of course, we need those kind of generation which can ramp up. Then we need a market to support that. We need workforce to support that. We need planning, investment, and operational paradigm which will support that. We need a better automated control and protection which will support that. And then thinking about all the key objective, which is reliability and operational reliability, which is security with diverse resources in there. So as a part of the PCERC, actually, we wrote a very good report, which is available for free to anyone. If you search for the PCERC initiative, you can get that future grid initiative. At the same time, when we look at the changes, actually most of the changes are happening in the distribution side. Transmission side, the polytronics has caused a lot of more control, fax devices and everything. But here, most of the changes in distribution, right? So we are seeing some unintentional islanding with DER because protection was not designed, or even voltage control in the distribution system was not designed to keep in mind that how the protection and control works. Once the DR will feed it, then the protection will misoperate. Same thing with the two-way power flows. Our protection settings need to be changed. Even though right now most of the feeder are still with the low penetration of renewables, but as things changes, all the control need to be changed or at least readjust. Then power quality problem with a lot of the changing type of load. We have more laptops, more computers, more computing devices at home, which is DC power. And DC power requires AC to DC conversion. And as we put more and more inverters in place, a converter in place, the nonlinearity of the power consumption will increase, and that will cause power quality to be changed and become a little bit worse, depending on that how much compensation and control we have placed in the load. And then operation with the multiple configuration will be another one, because especially with the DER, once we do the restoration in the power grid distribution system, we think about multiple configuration, which is possible by connecting, turning on and turning off the switches. With the DER, we have to be more careful that how we do the restoration. Of course, the two-way flow, we have to be careful with the crew member safety. When they're repairing things, they're not only getting the feed from this side, but they can also get the feed from this side, right, from here. And they need to isolate both sides before they do the maintenance. The production coordination with the renewables is changing with the high DR penetration. Missing link between EMS and DMS. One is a transmission system operation, one is a distribution system operation. What should be the information exchange between them? Because these are different owners typically. But if there's no link, this is now responding to transmission, and transmission is responding to distribution, because remember that all the loads are here. It's not here. While some generation are here, and the long distance transmission line is here. So how do we make sure that it's well coordinated, because the exchange and control is increasing in terms of how finer control timeline is. And as the control timeline is reducing, the exchange between information between these two also need to be done. So every disturbance in transmission does not need to be only cared by transmission, but also distribution. Every disturbance in distribution will be taken care by the transmission, but also distribution. So, which was not the case. If anything goes wrong in distribution, we typically used to take care of transmission, because the control was traditionally more in EMS side, not in the DMS side. With the increasing DERs, voltage regulator will not work as they are designed and set. So we need to adjust that and do more frequent control. We wish to do the voltage regulation sometime in a month timeline, right? Like you set it, and if there's no DER, you don't need to change again, because it will operate just fine, because you know the load profile. But if the load profile is changing like a duck curve, even at the distribution level, then you need to control voltage regulation settings more often, sometime throughout the day. Once we connect DERs, then of course there is a cyber system associated with that for monitoring and control, and that comes with the cybersecurity of DR value maximization and making it secure. Large number of control variables to be solved, because if you have more devices with which can be controlled, now you need to control all of them. So if you want to solve the optimization, it is more complex, because there are more number of variables to be done. Of course, we need to think about a different way of doing things: distributed control, decentralized control, centralized control. Then regulatory framework need to be also support that. Another big problem is the lack of visibility. If it's grid connected, then we definitely want that to be visible to our ADMS system or a subsidiary of ADMS. Without that, we don't know that what's going on, and we cannot respond to that. Storage is getting its way more and more in the system. And how do we maximize the value and use that as a flexible operation, especially because battery is probably one of the most flexible device, because it can operate in 4-quadrant operation. If you take the P and then Q, then this is positive P and positive Q. This is the positive P and negative Q. And then here is the negative P and negative Q, which is like a charging through discharging. And then the other one is negative P and Q. So the electronics, if designed well, it provides a lot of flexibility. Then balancing resiliency versus economics and reliability assessment. Again, resiliency is a very new term, which is slowly getting integrated. But there are a lot of conflicting, between economics. If you want resilient, you need to put more money, while objective is economics. But if if the event happened, it cost us more money. Then how do we think about economics for smaller system versus larger system or control? And the automation and asset ownership is also very important for that. Just showing that how solar impact. So if you were, last year we had this solar eclipse, which went through its path, and that impacted a lot of solar. And if we don't plan and are not prepared for that, it will definitely change the power grid generation and eventually the operation, right? So these kind of event does impact more and more as we put more and more solar. So to summarize it, we got this basically earlier this transmission system, which was generating at the bigger generation plant and sending the transmission, then sending it to the distribution to the load. It's changing. Now we have these renewable integrated here, more cyber system integrated here, and then we have so many communication towers, networking, more behind the meter kind of a solar rooftop. The load even have changed, like linear load, which is like a resistive bulb. We have now a CFL, which is more non-linear. We have charging station. We have power quality issues. We have a different kind of storage. We have a building with the net zero. So things are changing. And with that, the operation also is changing, right? So we have ADMS becoming more and more complex at the distribution side to control these DERs, which is the drums. We also have a microgrid system within the distribution system, which has its own control microgrid management system. So now if you at the transmission system, thinking about all of these, there are more active system eventually, right? And then we need to know that what's happening in transmission system to respond to anything that changes the grid operation. But another thing which comes with that is the digital transformation. As we can communicate and compute at a faster rate, and with all these massive sensor deployment, we have more data. We have more data that we know that what to do with that. And these data are coming from everywhere, right? So it's not only operational data. It is data from the images. We send drones to take images. We do thermal imaging. We know about transformer a little bit more because we can collect and even store the data. We know the historical IO analysis for the transformer. We have a smart meter data, a lot of those. We have different rate of data, power quality data we have. We also are getting data from satellite, right? Which will provide us the pictures or weather stations or space weather. We have power plant operational data, a little bit more and more, again, because we can bring it, we can store it, computing is cheaper, and that's why we're getting this information. We have a generation asset information. When was the transformer last repaired? Why it was repaired? Why the generation was repaired? What happened? Which will do that, but will not store those data. But now we do store because again, the storage of data, has changed what we used to do with the paperwork, which is still good to do, compared to a digital data set. Then control center operational protection data. We have a lot of evaluation data that we send our asset maintenance team to go and collect data, evaluate it. Sometime we do every 2 years, sometime every 1 year, sometime every 6 months, go and do the evaluation and make sure that it's still operating as it should, right? But we collect those data and again, we can store it. So those data is there. Then we have a lot of cyber data, and these are not comprehensive list. We collect lot more data. And with these data are totally isolated. Smart meter data is in different database, while transformer demographic will be in totally different database and maintenance will be in different database. Now we do need a data science platform which will correlate this data if we see that it should be related because it's coming from the same grid, same system. And then we need some AI community that what's going on with these and can they fix it in terms of making a better use of this data. So now we are looking at expertise, which is beyond the power grid, but we run into the problem that this community does not know about the power grid. If you don't know about the context where it's coming from, you will make a decision, you will process it in and tell us something which does not make sense. It does not follow physics, right? So there are a lot of challenges. Even though AI is very useful, it can help us. So I'm part of this SIGRE 2.52, which is AI application power report, will come out soon, being finalized, and it has a very comprehensive set of information about AI application in power. So it can propose action, it can prevent failures, it can provide insight, it can do the proactive control, it can do predictive behavior. A lot of different things. Possibility are limitless in control, maintenance, IT, market forecasting. The report is going to be several hundred pages, but pretty good. So let's look at the AI application. So what happens that our system, which is a power grid, which is now a cyber physical system, is very similar to any system that we know, either it's a biological system, physical system. And now if you go and look at the science scale, right? How we take the system level problem and solve it. What we do is that we model it. We model it so we can predict about that, right? And for model, we need to observe the real existing system. We look at that and say that, okay, now I know that these are the variables and this is how I can relate these. And we cannot solve very highly nonlinear higher order system. So we go with the second order, third order system, and which is approximation, but I can represent that. And typically it will represent well because the system was not very complex, right? So we go to second order equation and then third order equation, and then we get the behavior system. So it will match the system observation. And we said, okay, it's good, right? So we can solve the power flow now. But the same system is becoming complex. Why it's becoming complex? That I just talked about that. Polytronics, changing load, different event, market, a lot of renewable energy, demand response. It's becoming complex. And these set of equation cannot, so this is becoming complex. This is a complexity. Everything is becoming connected more and more. And as it gets connected and complex, we will not be able to use the same set of equation which was working very well because this was not a complex system in the past. My system is changing. So this same set of equation is going away from representing our grid as it. So if it is a 99% accurate or 95% accurate, now it is less than 90% accurate because system has become complex. At the same time, we are getting a lot of data. So what do we do with that data, right? Then we said, okay, let's apply machine learning, AI. But then we run into the danger of these machine learning and AI community not knowing about the system, the context. So what happens? We produce the output with this machine learning, but it does not follow the law of physics, right? And if it does not follow the law of physics, it's not useful. It's not useful for controlling and monitoring the power grid. So what do we do is that we look at alternate way of doing thing, and that's called physics-informed machine learning. And that's very much needed because we have to always respect physics, which operates our power grid. And even in the machine learning data science, we have to respect that, right? So here's the one example, this is a harmonic oscillator, which is very simple spring weight system. It has a response. If you try to solve that neural network, it will never solve it. Just simple second order equation, it cannot solve it. But as soon as you take the equation of these harmonic oscillator, you put that into the neural network, it will work perfectly fine and will match that, right? So here's the example, and that's what we want in the power grid also, right? So we have this big informative data, machine learning method, but the small physics, this is a one extreme where less physics and more data. And other thing is small data and full physics, right? So we used to do this physics-based method. We need a hybrid. We need a hybrid together to capture both. If you want to solve some problem, not every problem need to be solved by machine learning, but some problem. So realizing AI application in the power grid, we need to think about the constraint, which is specific to the power grid operation component, you know, and where it makes sense to apply. It only makes sense to apply, which is highly nonlinear problem, which our equation cannot solve, which our math cannot solve, which our physics cannot solve. And then when we look at that problem, we also need to make sure that cyber, which is information and cyber technology, is also supporting that. We have a data. If you don't have a data, then we can again not apply machine learning and AI. Security, storage, power requirement all need to be considered. And then most important thing is that, like I said, that machine learning and AI is a machine which is being learned. It does not understand the physics. Unless we embed that, we are not sure it can solve it, because AI is not explainable unless you make it, which means that validation becomes very important for a lot of different possible operational set. Applicability in long-term lifetime, what is the needed for the product that we make with the machine learning and AI, and also does it consider the ethical constraints, because whoever is designing this AI machine learning is not being approved by the community, right? Which means that it might have bias, because anything that you make it will learn it, but it might have a bias. So all these things need to be considered. We need to consider jurisdictional requirement, that who owns the data while using it. And then we need to understand that if we want to do most of the thing with the machine, then how a human performance comes in, which is the power grid operators. And so far, things are going to change, but right now, application, if it's very complex, humans are still more effective, because anytime you want repeated task, machine is good because it can do things with anything which is repeated again and again. It can learn, and not very complex machine are most effective. In between, machine can augment the humans, but if the application becomes more complex, which is not repeating itself, but a lot of data need to be considered, a lot of physics need to be considered, then humans are more effective. And if it is a high scale and high complex, then none of them effective, because humans will become overloaded. Machine cannot learn because it's not a repeated task. So that's where we don't have a solution. And that's how blackout happens. That's why power outages happen, other than economic constraint that cause power outage too. And we have seen this in the past, right? Anytime we have the new system, it will have a problem. Like 2001, we had an autopilot, a lot of plane crashed. We had automated electric vehicle or automated vehicle with the advanced driver assistance system. We had more crashes during that time. A lot of time we have like a Tesla is of course autonomous machine, but if the driver does not pay attention, there will be a problem. So there are a lot of limitations in terms of inaccurate data, insufficient data, especially if it's a multi-rate, multi-type, varying data sources, multi-owner, privacy consideration, bias limitation. We have a human in the loop with the bias, which we already talked about that. And then we also have a domain limitation, which means that explainability. If you design something with the AI, we cannot explain that why it's doing some things in specific way, right? Power grid is very highly biggest man-made machine ever. It is very nonlinear in some observation, and that's why the same concept does not exist. So if something is normal versus abnormal or anomaly, the definition of that is also going to change. So continuing with that, where the data is coming from is very important. What is available, what it will activate is very important. Different data sources, attributes, how the data is collected, how it's being stored, what is powering them, We now have a big data center. There's a news all over that Visakhapatnam is going to get 15 billion or even several $billion of data center, right? So data center, when it comes, it basically tells how it's being stored, what kind of things is being processed. So we know the limitation of that computational aspect of data, and that will decide that. So let me get to the last part. Physics informed machine learning we talked about. You can embed physics into the machine learning, which I think is very important for any power grid application. You can embed that into the loss function. You can do the fine tuning with real world data, which already follows the physics, right? Because it's coming from the real system. And then you can also, so that there are different ways that you can do that. You can use the physical model, which is basically getting the input, and data is being generated from the physical model. So of course, if you feed this data, it also followed the physics. So these are two different ways that you can embed the physics into the machine learning. If you have something like a reinforcement learning, then you can have a more opportunity to embed the physics. Either it's a discrete variables or it's a continuous variable, or it's a reward, right? So reward and penalty can respect the physics with this reward solution equation, where again there's a physics and math embedded here. A policy, you can embed the physics and math, and then the environment, which is being used to generate the data, or feedback signal, can also embed the physics. So depending on the technology you're doing with the unsupervised, you're dealing with supervised learning, you're dealing with semi-supervised, you're dealing with reinforcement learning, all has a different way to embed the physics. So let me talk about a couple of applications. So this one is a real-time detection of event, which of course a status machine can do, but it's slow. And if it's a dynamic event, a status machine cannot detect unless it is a dynamic status machine, right? And if you put that logic into that, even if it detects, it will not tell you that what kind of anomaly it is. And I think that's where the AI and machine learning is more useful. At the same time, we thought that supervised is not needed because of data drift. So it's a unsupervised method, very simple method, which is fast enough, can be done, right? So we did this anomaly detection, then anomaly classification, then event classification and localization. Is a good application. We developed and worked a lot on this with a different technique where machine learning is very useful. So if you look at the event, you sometime you have like this response. We definitely know it's an event, but sometimes there are outliers which means the data itself has noise and wrong and drop data, and these are all anomaly. We need to detect these things and then classify it that this is a bad data and this one is the event data. Then we get to this anomaly detection with the concept drift, where the definition of anomaly is changing over time. Now, if you look at, let me just simulation result from here. So this is the concept drift is considered. Of course, we get better result and accuracy in anomaly detection and classification. I'm not going to detail of these because we have written a lot of these papers, which these takes years and years to develop something, but what is important is their concept, that how it works, and that's what I'm going to discuss it. So here, the same physics-aware machine learning is working, but now it's working with the data drift concept, which is called concept drift. For generation data anomaly, it's more challenging problem, and we need a differential equation and to be embedded into the neural network. So we developed this MNPIN, physics informed neural network, where differential equation are embedded with the algebraic equation, and now it can detect anomaly at really, really fast time scale, even at the generator. Right, so these are the set of equations that you need to embed, but now it is able to detect anomaly into the dynamic system response. So a new integrator cell and new algebraic cell was, proposed. And then comes so that was a, physical PMU data set, like and a SCAR data set. So you also have a cyber data, which is coming from these, automation controller, IEDs, intelligent electronic devices. And this is all cyber data packet, which is either in 37.18 format, which is PMU data, either DNP3 or GOOS or sample values. And you can get all these set of data, from the real devices. In our case, it's tied with the power system simulator because we have a more control over that, where all these data are either structured or unstructured, or time series, or streaming or non-streaming. Sometimes it's a static, sometimes it's dynamically changing. You take those data and you can also apply machine learning and monitoring. Here we cannot apply physics inform because it's a cyber data, and cyber data does not follow physics, right? It's a data packet, and it's tied with the cyber system, and of course that's not a physical system, right? So in a way, power grid data anomaly, we have advantage. We have advantage because it has to follow physics, while cyber data, which is a discrete data packet, we are in disadvantage because it does not follow physics, but it does follow a rule base. It does follow a structure of DNP3, which we define it. It does follow 37.18 format. Whatever format IEC 61850. So it has to follow that format, and that's what can be used to, once we get this set of data packet, then also log file, a lot of log file which we need to parse it, and then use it to process and detect anomaly in the cyber data. So we use this text, which is from Idaho National Lab, to convert this output into a cyber threat intelligence report. We also used NLP, natural language processor based digital assistant for grid operators. And we have been modifying this to another digital assistant, which is now with the large language model. And again, just making the operator for easier and easier. So this cyber data anomaly detection tool, we are using a lot of different approach, autoencoder transformer. Again, it does not follow physics, but it does follow the domain knowledge from this, knowing that what kind of data it is, where it's coming from, and we can process it. Other thing is cyber resiliency, which is looking at system and telling some kind of score that how resilient the system is. So we have worked on a lot of different resiliency tools. This one is one where you have a distribution system with a lot of DERs. We first take the services from here. We call it IoT resources, and then say, okay, should we trust it or not? And then the neural network autoencoder was used here with the federated learning for trustability score. Then we used the primary node resiliency PNR, which is basically based on a lot of these factors. So resiliency is, again, ability of system to keep supplying load even with extreme event like a cyber attack or cyber failures, right? So what are the things that will stop me to become resilient, right? It is basically, do we have enough generation? Do we have a critical load, and what is the location of that? Is it connected to the system? Do we have enough ways to reach to that load to supply the power, right? So connectivity redundancy. Then device and communication vulnerability. So all of these things were considered, and then we get a resiliency score at this primary node. And then we go to all the way to distribution system by integrating all these things with the multi-factor criteria. Again, this is something that we took years and years to develop this approach. And if you're interested further, you should read a couple of papers where we have developed set of equation for IIT trustability score, and then this privacy preserving PNR, which is a primary node resiliency score, and then finally distribution system resiliency score for each feeder. And then once we got this scatter data anomaly score, we got PMU data anomaly score, we got cyber data anomaly score, we can combine this to tell us that this is the cyber failure, this is a cyber intrusion, this is the weather event, it is a sensor failure, is it asset failure? All of these can be done because you are getting so many different stream of data. And once you know that this is an anomaly, this is an event, and this is a bad data, then you can also, the event and bad data impact, you can rank it. You can rank that which is causing more problems. I see 10 different event happening in the system. Which one is more important? And then we can compute all those things with the resiliency metric. That's just like a contingency ranking we used to do. And this resiliency metric will rank it and will tell the decision support that which one to give more attention, which one to solve it. So that's what we do with the sync ADC, EMS, and ping things. And then finally, we get to the structural awareness and decision support. Another approach, which is related to the real-time data processing, is we can use it for physics-driven proactive stability control. So idea here is that we get the PMU data, and based on their dynamic response, if I have a physics-informed neural network, I can predict that how the next data set will look like. If I can predict it, and if that is going to be instability, if it is going to be unstable response, and if I can predict in advance, even like a few milliseconds before, then I can take a control action and stop it, right? So we can take a proactive stability control. That's what we do. We are able to predict that it is going to be unstable response in the future. And if you take a control, you can go back to the stable response. So you can see that this is really, really quick, starting from the normal working to the event happens. Of course, any stability will happen because of event, and event need to be isolated because we predicted with the federated inference. And that was another thing that we did. We did the prediction, but we did the federated prediction, which means that machine learning was working in each area and coordinating with that. And then with the oscillation and stability and proactive control, we will take the remedial action and make the system from unstable, which is not even observed, it's going to be in the future, to stable even before it happens. So this is another a good example of physics-informed machine learning and data-based stability control. You can also, which is very important to know that what is behind the meter, so you can take the proper control actions, right? So we use this BDM PV estimation, worked with Hawaii in this case, and then it is able to predict what's behind the meter with no sensor. So we don't have sensor there, but we can predict it very well because we got so much of data. We got voltage current power meter from higher level, which has a signature of those behind the meter resources. We got some satellite images, so we can predict the cloud. We can see the the basically sun, so how much sun is shining. So all these things we can get it from satellite images. And we also have a lot of ground cameras and weather station, which will give us the data. And then from there, we were able to apply some machine learning, which is also physics informed, to do the prediction behind the meter. It was very accurate. Another one, we can also use the same thing because once we do the detection classification, then some of those things will tell you that asset is a problem, not the sensor, and there's no event. And if the asset is a problem, which is happening here, then how do I, which is not causing a big problem right now because it's only a smaller problem, it's not a fault, and these assets need to be fixed, right? So for that one, we have used this conditional generative adversarial network, CGAN, with some data already trained. We are still continuing this work, but it can help us with the detection and classification for solar asset monitoring. It can minimize the PV downtime. It can also guide the repair and maintenance. We're working with our own utility, First Energy here. And all these things need to be validated. So we do have this, real-time hardware in the loop where we can generate the data at a really, really fast rate with RTDS and Typhoon, with the power electronics. We have a microgrid controller here. We have a distribution system. We have transmission system model here. And then we have a control room which we can reconfigure as a ADMS, or we can configure it as a EMS. We can even configure it as a network operation center. That's why we have all these tools like Splunk and Snort. Ping is a software for PMU data collection. NS3 is the network operation center. And we can also see that how power grid operator will respond to different kind of disturbances that is happening in the grid. So we have this eye camera where we can see that where they are looking at, like a heat map. We have a stress monitoring in the system, which we can then see that how stressed they are while operating the grid in different response. And we actually simulated that. We had a real grid operator coming into our lab so that we can tell them that what action to take. So we tested and validated, a lot of these application in the lab environment. So just to summarize, I think ML machine learning is going to help a lot, but we're not ready unless we have enough data set, and we have to find a good match between machine learning approaches and analyzing the power system problem where it's really applicable. We don't apply where set of equation with the physics can still solve it, right? If you want the faster response, then it's okay to apply machine learning, but machine learning should be with the physics informed. Of course, data-rich problem, machine learning is already being used. So if you do forecasting, it's already being used from several decades. If a model is available with rich data set, that's where it make more sense to apply the physics informed machine learning. If the model is available with no data set, of course, you cannot apply machine learning. And machine learning will not give a good result for a very highly complex and dynamic problem, like a transient stability or contingency analysis, because it's a very high nonlinear problem. So I think that's not a good application yet, but in the future might be. And the most important thing is the validation metric. So we are in the data-rich environment now, which is slowly changing. We are getting more and more data, and complex and dynamic problem is still open. It has not been solved in real time. We have solved in the planning, but not in the real time. If we develop a new technique, which is physics-informed machine learning, then validation and metric is very important while considering the human aspect, which can make a decision on that. And cognitive science approach of cognitive overload and cognitive flexibility should be considered while developing these tools. So I'll be very happy to answer. I think we have only 7 minutes left probably, but I'll be happy to answer any question if you have.
Thank you so much, sir, for the excellent session. Now this session is open for the question answer. Participants, if you have any question, you can ask or you can write it in the chat box. Any questions from the participants? Okay. Okay, sir. I have a question regarding the human factor sensors that you have shown in the last slide. So exactly like to analyze the stress on the person. So how exactly you are applying the machine learning models in there, and what are the information we are capturing there?
Yeah, so these are two different things. So once the tool is working with EMS function, and the other tool which is working with machine learning, physics informed machine learning, then we basically simulate like a, let's say, cyber attack or something like extreme event.
Okay.
And then we see that how human operator is responding to that. As we expect, their stress will increase because they don't have these extreme events that they are not trained. And if they're not trained, then their stress basically tell us that we need to provide them more information and only what decision to take. So then we develop tool which will help them to make a better decision. And that's what we wanted to see, that where So another thing is that the eye camera, which is the glasses,
Mm.
that where they're seeing it, and if they're not seeing the right information because it was a stress scenario, they will not make a right decision. So that's what we trained for after that, and then we developed some tools which we call resiliency assessment and resiliency decision support tool, and then said that now make a decision. They were able to do so. We did
Okay.
that experiment and published that work. Yeah. I see that someone has also asked
Yeah,
question in the
in
chat.
the chat box.
The first one is that data from PMU comes in EMS. So PMU goes to the PDC, PDC goes to the open PDC. In again, there are a lot of different configuration in different system, and then it can be embedded into EMS if it is a hybrid state estimator. So there are software from, let's say, GE and other vendor which bring it into the EMS because it's a hybrid stress estimator. If there's no software or no function that exists for PMU, then PMU data will not be coming to EMS. It will be separate and will be used separately with its own software. So it basically depends on which power grid, which software we are talking about. Then the next question is that how we protect system from solar storm and wind storm with control. Yeah, so this is a good question. Like basically when these happens, we cannot protect our system in real time. So everything that can be done is before and after, which means that before, if you know that this is the area where storm and windstorm comes very often, you can make it stronger and reinforce it, right? But other than that, we cannot do much. It will damage when this event comes. And then the thing becomes that we cannot protect that part because it's going to be damaged. Then how do we protect and control the remaining part? Which means that this disturbance should not cascade. It should not impact beyond what we already have. And for that one, isolation is important because it's already damaged. So we need to isolate that damage, whatever the system is, which has been damaged. And then we need to, because these are kind of thing we can typically predict in advance. So we need to balance the energy between the available supply and available demand, right? If we are able to balance that in real time through control, then the system damage will be, or system will disturbance will not cascade. So anytime the solar storm, windstorm happens, unfortunately, there's no way to save that part where the storm is going to damage, unless something are done for reinforcing it, physically making it strong. So then the focus become in real time how we isolate, just like a protection, how we isolate that and keep the remaining part as balanced as possible. There are a lot of ways to do that. Islanding some part, connecting some other part, and making it proactive control and faster control.
Okay, I think there is no more questions. So we can conclude here. Thank you so much again, sir, for this excellent session.
Thank you.
So if you can send the PPT after this presentation, that will be very helpful for us. So we can upload, we have to upload it on the AICTE website as well.
Okay, sounds good.
Thank you. Thank you so much.
Thank you.